So let me write them again. You said
h of x
h of x
equals minus f of x.
Okay.
And and according to the source I have, that's a reflection over the x-axis.
Correct.
And then the second example, h of x equals f parentheses minus x. And that's a reflection over the y-axis.
Correct.
What's a good way to remember those two? Because they look so alike, it's easy to get confused.
Very good. If you remember last time when we talked about transformations, was said, when we look at the function, the first thought is, what is changing? Right? Is it x or is it y? If the transformation touches x, x is changing. If the transformation touches y, y is changing. In this case, the transformation, this sign touches x, does not touch y. This is y. In this case, it touches y. It does not touch x. It cannot be both at the same time. So it's very simple. If it touches x, it's a reflection with respect to the y-axis. If it touches y and not x, must be a reflection with respect to the x-axis.
And the example that they give is x squared
with a negative x squared.
Negative x squared,
right, but that's not a good example
right.
to work on these two. Here's why. Right. That function is not a good function for this particular transformation. Because if you talk about this, it's still x squared. You haven't shown a transformation here.
Okay.
So that's not a good function. It is a good function for this one, though. Because if you want to look at this, that is very clear. X squared opens upward, and this is x squared. And negative x squared must open downward.
Which reflects over the x-axis.
Exactly. And this does not touch x. This would have been touching x, right? This touches x, but this touches y.
So what's a good example of the second one?
Yes, it's the one that I gave in class last time. This is the best example with the functions we have. Is one function, f of x, and then g of x. This is the perfect example for what you're saying. So always look at the examples we do in class because they're always useful. So when you analyze this, you know that the base function is the square root of x. And now compare these two. What would you say changes? Is it x or is it y?
X.
Yes, because this negative sign touches x. What about this two? What changes here? Not x, because this is identical. It's something completely outside, not touching x. So this is a transformation. So when we graph those, this is the square root of x. And this must be this. And this one must be this. Is that better?
That is better, but I think I have to do some more examples.
Yes, of course. Of course. Of course. Of course.
I'm guessing we're going to see something like that on the test.
Well, you're going to have something simple to worry about, not necessarily a difference between these two. Thank you. Very good question. Anything else? Other questions for me? Okay, so we are back to transformations, and I think we're done with that actually, but I would like to, before we look at substitution, I would like us to just select a couple more problems with transformations. And I got it, it's right here. So I'd like to look at just one more problem from the book with transformations before we continue. with systems. As I said, whoever had this idea was brilliant, but who put it in practice, not so much. Okay. I'd like to look at one more combo, and I don't want to waste your time till I find it. There is no point. I can make one up. So let's take a look at f of x equals negative the absolute value of x plus 1 and plus 4. Which base function was used to determine this function? Which function did I use to create this function from the list of functions? Absolutely, thank you very much. What is the first transformation in order of operations? The first transformation in order of operations, I'm going to copy it here, is what? How do we think about it? What is the correct order? Jay, go ahead. We have to, let me write it down. Graph, sorry about that, using transformations. This is the requirement. Graph using transformations. The transformations have to be presented in the order of operations. Let me also write that down to make it very clear. Transformations must be presented in the order of operations.
So logically, I'm thinking maybe you're going to start with what's inside the absolute value.
Of course, because this is exactly, the sequence is exactly as if you would evaluate the function. So if I ask you evaluate the function for 5, you will have to perform 5 plus 1 first. Then you will have to multiply by -1 after you apply the absolute value, of course. And then you have to add 2. This is the correct sequence of transformations. So one more time, what is the first transformation here then?
Absolute value of x plus 1.
Yes, so it is x plus 1. What does that do to the base function? So 1 is a transformation on the absolute value of x. What does it do?
Kind of shift it up, I think.
Careful, we are changing x. If we change x, we cannot go up.
Okay, that's right. That's true.
If we're changing y, we go up or down.
Yeah, I guess that's true.
But if we're changing x, it has to be on the x-axis.
Right.
It is not to the right, careful. Think in terms of the x-intercept. So the absolute value has the x-intercept at the origin. Where will x plus 1 have the x-intercept? Not at 1, because 1 plus 1 is 2, and the absolute value of 2 is not 0. But where?
The only other choice is
Where is this 0?
the -1.
Exactly. So this is a left 1. Left 1 unit.
It's very tricky.
No, just think in terms of the x-intercept.
Okay.
So if I have x minus 3, where will the x-intercept be? Not at -3, for sure. Because -3 minus 3 will be -6. The absolute value is 6. It's not 0. Right? So where will it go? This one.
Over to 3.
Correct. Right 3. What about x plus 4? Where will that go? Not at 4, because 4 plus 4 is not 0. So this will be right 3, and this will be
Left 4.
left 4.
So basically what you're doing is you're setting that x plus 4 equals to 0.
Exactly.
And then solving for x.
Yes.
And that's where the burden is.
Because it's a transformation in x, it doesn't go up and down. So I need to know where it lands. So if it's x plus 1, it has to land to the left. If it's x minus 3, it has to land to the right. Because it's only, we cannot have two transformations at the same time. If it's a transformation on x, it cannot go up or down. So if I put negative 3 here, y is 6. It means that it went up. And that's not what we are trying to do, right? Okay, perfect. So now the next transformation is the absolute value of x plus 1, but with minus in front. And this is a transformation on 1. What does this do to this? And you have to think in terms of, do I change x or do I change y? Yes, we are changing y. In which way? Careful. We're multiplying. We're multiplying by negative 1. Reflection with respect to, we're multiplying y by negative 1. So when we multiply y by negative 1, it's a reflection with respect to the x-axis. So reflect with respect to the x-axis. Because we're changing y. It's outside. The negative does not touch x. It's outside of this function. And number 3 is a transformation on number 2, negative x plus, 1 plus 4. What does this do to number 2? You have to decide what changes. This does not change. So what changes? Does it change x? Does 4 touch x? Or does 4 touch y? Yes. So it's up 4. Is that clear? So one more time. We can already picture the graph before we even graph it. This is the absolute value of x. Then you tell me to move 1 to your left. You told me to reflect and then move up 4. Can you tell me the range of this function? We haven't even graphed it, but we know the range. What is its range? One more time. The absolute value of x, 1 to your left, reflect with respect to the x-axis, up 4. What is the range of this function? From till? Till? That's it. And we haven't even graphed it. But we know transformations, we know the base function, and now we can picture this in our heads already. Does it make sense? Now let's graph all of them. We start with the base function. Here's the base function. It bisects the first and the second quadrants. Then you told me to move it 1 to the left. So this is the absolute value of x plus 1. Then you said, now reflect. Okay, I'm reflecting. And then he said, what? What did you say last? Very good. So 1, 2, 3, 4. So this is final. F of x, negative x plus 1 plus 4. What if we want to find the x and y-intercepts algebraically? You already gave me the range. So you said negative infinity to 4. What if I want to find the x-intercepts and the y-intercept? How do I find, for any function, the y-intercept? For any function, when we want to find the y-intercept, what do I set and equal to what? Very good. For the y-intercept, we find f of 0. Let's do this together. 0 plus 1. 1. The absolute value of 1. 1. 1 times negative 1. -1 plus 4. Very good. So 0, 3. Do I have here 0, 3? Maybe. Remember, graphing with transformations is just a quick graph. It's not a perfect graph. It will never be a perfect graph. We just want to picture the graph in our head quickly. So that should have been 0, 3. Even if it's not exact, it's fine. Good. So how do I find the x-intercept for any function? Excellent. Great job. How many x-intercepts do I have to find? Excellent. 1 here, whatever that is, and 1 here, whatever that is. Good. Okay, so let's see. So I have negative x plus 1 plus 4 equals 0. First step. What should I do with this? I'm solving it for x.
Move the minus x minus plus 1 absolute value to the other side of the equation.
Yes, that's perfect. Or perfect. Or this. But you're right. If I had done that, I didn't have to multiply by -1 or divide by -1, because now I have to do it. We clean this up completely. Absolute value is not a grouping symbol. You cannot touch the inside. You cannot do anything to the inside. Now, what do we know from the previous course? What are the options now? One option is, remember how we think. What can I have here so that the absolute value is 4? What number? 5? No, because the absolute value of 5 is not 4. -3? No, because the absolute value of -3 is not 4. What should I have here inside? What could this be for the answer to be 4?
4.
Or, very good, Morgan, or there isn't one other number whose absolute value is still 4. Which number?
-4.
Excellent. So x plus 1 could be 4, or x plus 1 could be -4. There are two possibilities. This is not a linear equation. The absolute value equation, do not treat it as a linear. It's not linear. Good. Is this clear? So when we have the absolute value of an expression equals a number, there are two possibilities. The expression to be the positive number and the expression to be the negative number. These are the two options when the absolute value equals a positive number. If it's 0, there is only one option. If it's negative, there is no option, because the positive cannot equal negative. So then from here we have that x equals 3, and from here that x equals -5. So the x-intercepts are 3, 0 and -5, 0. I don't know. So this is 3, 0, 1, 2, 3, 4, maybe. -5, 0. Not perfect. Any questions about transformations? Do you think we can move on? Do we need another example? Are we okay? Yes? Okay, so in that case, we're moving on to systems of linear equations by substitution and systems of linear equations by addition. And that will be the end of topic 1, and we move on to topic 2. But then I would like to go through the factoring supplement that I gave you last time before we continue with that. Okay, so let's take a look at 10.1 and 10.2, solving systems of linear equations by substitution. And the other method, they call it addition. That's fine. I call it elimination. It's the same thing. So substitution and adding, which I like to call elimination. Okay, solving systems of linear equations. We're not going to do graphing, so okay. So they say I should show you at least one example with the graph. So let's do one example with graphing, and then we do the other two. So let's start with graphing. They didn't say that, but they just put it in fine print. That's okay. Okay, so let's take a look at an example. And I'll let you choose. From 11 through 42. Let me choose the first one and then you choose the next one. So let's say 16. 16 is on your page 775. I don't know how that works in your book. I have no idea if it's in the same order. I'm assuming it's in the same order. Okay. So the system is x plus 2y equals 2. And y minus x equals 4. They want us to solve by graphing. Solve the system by graphing. I will personally never solve a system by graphing before I determine the algebraic solution. I will never do that. And you can ask why. It's because it's difficult to read from the graph. So I will get the correct solution, and then I will graph it. I will still do what I'm asked to do, what I'm supposed to do. But first I will solve the system using any algebraic method, and then I will graph. Okay. So first of all, notice that this equation and this equation, they are both what type? Very good. So in order to solve a linear system, let me refresh your memory. What are the options? So 3 options. Every time we solve a system of 2 linear equations in 2 variables, 2 linear equations in 2 variables, there are 3 possibilities. This is one possibility. This does not mean a perpendicular or anything like that. It just means that they meet in one point as the solution. The second option, no solution. They do not meet. They are parallel lines. And the third option is this is the first line, and this is the second line. Infinitely many solutions. They are the same line. So they overlap completely, which means they have infinitely many points of intersection because they are the same. Okay, so as I already mentioned that a few minutes ago, there are 2 algebraic methods that we talk about it in this course. There are many more. Kramer's rule, determinants, inverse matrix, all sorts. But in this class, we basically look at 3. Graphing, elimination, or I should say first substitution and then elimination. So in this particular case, I will find the X and Y-intercepts for both and graph them. So let's copy the first function, linear equation. Let's determine the X and Y-intercepts. When x is 0, please cover x and give me y. You do not have to solve for y. Do not waste your time. There is no need. So when x is 0, please give me y. Very good. So then 0, 1. Now when y is 0, please cover y and give me x. I covered it because it's 0. That's the only reason I covered it. So then x equals, say it again. X equals, when I cover y, x equals, of course. So then 2, 0. So let's graph this line, plotting the points as we did before. So 0, 1 and 2, 0. I connect and extend the line. Please write the name of the line, the equation, in other words, so we know which one is this. Then we go back and we proceed accordingly, same thing, same steps, with y minus x equals 4. When x is 0, how much is y? Very good. So 0, 4. And now when y is 0, how much is x? Excellent. Thank you, Morgan. Perfect. So this is what we have, 0, 4 and negative 4, 0. Let's plot the points. Negative 4, 0 will be this approximately. My graph cannot be perfect. And 0, 4, 1, 2, 3, 4. So here's the line that we will call y minus x equals 4. We see that the line intersects in one point. The lines intersect in one point, so it's the first option. The system has a solution. It's not like this one, and it's not like this one. So these two systems are called consistent. They have solutions. This one is called inconsistent, no solutions. So consistent system, consistent system, inconsistent, inconsistent system. No solutions. So we know the system is consistent. It has a solution. I don't know. I will say negative 2, 2. But I'm not sure. I have to go back and check. Back to the system. I'm going to copy the system here again. X plus 2y equals 2 and y minus x equals 4. So we have to check. This point has to verify both equations, otherwise not the solution. I have to go back and do something else. Graph again, who knows? So x is negative 2, y is 2, x is negative 2, and y is 2. So let's try. Negative 2 and plus 4 is 2. Lucky me. 2 and plus 2 is 4. Yes. So indeed, negative 2, 2 is the only solution, and no one can find another. And this is x, y. However, for the same system, let's talk about substitution. So let's work on the same system. We know the solution already. I copy the same system one more time. And now I would like us to use substitution. We use substitution only for a variable that has 1 as the coefficient, or negative 1. So we can substitute or solve, in other words, the first equation for x, and the second one for either x or y. But no, I don't recommend you solving the first equation for y. Okay? So therefore, which one would you like to solve for, and which variable?
solve for y in the second equation.
Excellent. So if we want to solve for y in the second equation, then this is the second equation now. We moved negative x to the other side. And then we have to replace y by what it equals to in the first equation. So now the first equation becomes x plus twice, in parentheses, x plus 4 equals 2. We know how to solve this equation because this is a linear equation in one variable. So what would be the next step? What would you do next to find x? What should I do? I have an equation. How do I proceed? I need to solve for x. What should I do? Distribute, of course. I just want you to tell me what to do. Of course. I have to distribute. Now what is the next step?
Combine like terms.
Of course, excellent. So 3x, and then I move a to the other side and I get negative 6. Excellent. And finally I get x to be? Very good. This is good, but not good enough. I have to go back and solve for y.
You can choose any equation.
It doesn't matter, but since I already have it solved, why would I go back to the original? I have to go back and check in the original problem anyway. So this is the easiest thing to do because I already have it solved for y. So we plug it in and we get y equals exactly what we expected. This is the method of substitution. Any questions? Any questions? Questions?
In the case that there was no solution, what would you have gotten?
Excellent. Great question. So here is an example. Okay, this is our system now. We want to solve by substitution, let's say. What would you like to do here? You can substitute for anything you want. X or y in the first or x or y in the second, because they all have 1 or negative 1 as the leading coefficient or coefficient. So which one would you like to substitute for? I will substitute for x in the first one. So I solve the first equation for x. And then now I have to put this back in here, in the second one. Copy the negative sign, in parentheses, negative y plus 2 minus y equals 4. A linear equation in y this time. What will be my next step?
Distribute the minus 1.
Excellent. So then I have y minus 2 minus y equals 4. These two go away. And I'm telling you, negative 2 is the same with 4. Would you accept that? No. So then what would you conclude about this system? Inconsistent, parallel lines, it must be. We know that. If the system is of two linear equations in two variables is inconsistent, the lines must be parallel. Which means they have the same what? Two lines that are parallel must have the same. Excellent. Great, Jay. Thank you. So inconsistent, parallel, inconsistent system, parallel lines, no solutions. Let's also look at one more, and then we'll look at the adding or the elimination method and some word problems. So let's say we have x minus 2y equals 4. And negative 3x plus 6y equals negative 12. Let's say we want to solve for, we want to solve using substitution. I would normally ask you to fully simplify both equations before you start, etc., etc. But let's say we don't do that just yet. And let's say we want to solve using substitution. What should I do?
Well, based on the guidance you gave us earlier, you would choose solve for x in the first
Excellent. Yes. I have to choose solve the first equation for x, absolutely. So this is 2y plus 4. And now I will replace in the second equation x by what I just determined from the first equation. In other words, by 2y plus 4. So then I copy the first equation, and then the second one, negative 3, 2y plus 4 plus 6y equals negative 12. Okay, how do I solve the second equation for y? That's an equation, a linear equation in one variable. What do you think we should do? Anyone? The same thing, right? So negative 6y, negative 12 plus 6y equals negative 12. And look what happens now. I did not determine x, but I got a true statement that is always true, always valid, no matter what x and y. So what would you say about this system? It's case 3, infinitely many solutions.
Another way to say that is the lines are collinear.
Collinear points, they are on the same line, but I'm not sure whether we can use the collinear lines. We can say identical lines, but I'm not sure. I've never heard that about lines. I've heard about points. So how do I write the solution, however? There is a method of writing the solution. X is anything that is 2y plus 4. So the points will be 2y plus 4 for x and y for y. This is the way we present the solution for a system that has infinitely many solutions. So I would like us now to look at that 8.1. And look at some more problems. After we look at systems. Actually, with your, Tim, with your class, I'm going to do this after chapter 4.
Pay attention.
So, yeah, pay attention. Okay, so we looked at substitution already. I'd like us to analyze elimination. So addition method or elimination, the same thing. So let me explain on an example, and then we can look at some more problems. So let's suppose we start with a simple one like 24. In 24, we have 2x minus 7y equals 2 and 3x plus y equals negative 20. You can say we can use substitution. You will substitute only for this, right? You will solve this equation, the second equation for y, and then you'll replace in the first equation. But that's not what we want to do now. We want to use the so-called adding method. Now we have to make a decision before we decide which variable to get rid of or eliminate. So I see here for coefficients, I'm looking at coefficients. I'm looking at a coefficient of x and I see a 2 and a 3. If I want to eliminate x, I will have to come up with the smallest multiple, which will be 6. So I will have to have here 6 and here negative 6, or vice versa. Here negative 6 and here 6. For these two terms to go away. A positive 6x and a negative 6x will make a 0, or a negative 6x and a positive 6x will make 0. So that's an option. Let's look at the second possibility. If I want to make y disappear, I don't need to multiply both equations. I only need to multiply one of them by what? And which one? To eliminate y.
By 7.
I will multiply the second equation by 7. Very good. 2x minus 7y equals 2. When I multiply by 7, I have to multiply everything, each and every term. So 21x plus 7y equals negative 140. And now when I decide to add, and the question is, okay, I'm adding those two equations. Why? What allows me to do that? I know the purpose. The purpose is to eliminate y. I know why. But am I allowed to do this? So here's the explanation. If I'm given an equation, 2x minus 7y equals 2, can I add 5 to both sides? It's not going to help. But am I allowed to add 5 to both sides? Will I change the solution if I add 5 to both sides? No. But what I want to do is, I want to add these two. This is negative 140, this is negative 140, and I decide to add negative 140 to both sides. In different shape, in different forms. But this is negative 140, this is negative 140, and I'm adding this portion here and this portion here because they are equal. And at the same time, it serves the purpose. This is the purpose. 21 plus 2 will be 23, and negative 140 plus 2 will be negative 138. So by adding, or if you want, you can say that you are adding this here, which is 2, and you're adding this here, which is 2. This enabled us to determine an equation in x, and now we can solve for x. Negative 138 divided by 23. Any questions? Any questions? We're not done. We only determine x. And now we have to go back and determine y. And then we have to go back and check in the original problem. So it's not done by any means.
That fraction is minus 6, by the way.
Say it again.
The fraction is minus
Yes, we have to simplify that. Very good. So x equals negative 6?
Yeah.
Perfect. So now we go back. It doesn't matter where. You tell me you want to go back to the first equation or the second equation. It doesn't matter. Which one? I would prefer the second one because 3 times negative 6 is negative 18 plus y equals negative 20. And when I move 18 to the other side, I get y equals negative 2. So then it appears, not guaranteed, it appears that the solution is negative 6, comma, what? What is the solution? Very good. We all see that. It comes with a question mark because I don't know. I haven't checked yet. I'm going to copy the system one more time. So 3x plus y equals negative 20. And now I will substitute -6, -6, -2, -2. If the solution works in both equations, then I'll say yes, that's fine. It is the solution. If it doesn't work in one or both, then it's not the solution. So let's check. So this is -12, and this is +14. But -12 plus 14 is indeed 2. Here is -18, and -2 is indeed -20. So now I don't need anyone to say whether or tell me whether it's correct or not. I know it is. Questions? Any questions? Okay, so let's look now at a word problem. I'm selecting the ones that they recommended. We can select any problem, of course. So they said 68. So let's take a look at 68. Any questions on this problem? Any questions on how we checked? Anything here? Okay. So the graph shows that from 2000 to 2006, Americans unplugged landlines and switched to cell phones. Okay. So this is the line increasing slope for cell phones, and this is the line, the landline, decreasing slope for landlines. Use the graph to estimate the point of intersection. Okay, so let's use the graph to estimate the point of intersection. What would you say roughly? In 70 years after 1970, 70 years after 1970, which is I think they meant here, yeah, 1990. Okay, so I think it's years after 19. I'm looking at a different graph. I'm sorry. 2000 to 2006. I jumped over there. I'm sorry. That makes because it made no sense. I said, what are you? Yeah. Okay. I was looking at a different graph. Sorry about that. So in 2004. We would say roughly number of customers in millions. So they were kind of equal in 2004, and the number of customers roughly, what would you say? I would say almost exactly in between, or maybe 180 or 175. Difficult to read. In 2004, about 175 million or 180 million. Okay. Part B, the function models the number of landlines. This function models the number of cell phones. Use these models to determine the year, rounded to the nearest year, when the number of cell phones and landline customers was the same. We already determined, but they want us now to use the substitution or elimination. According to the models, how many millions of customers rounded to the nearest 10 million were there for each? How well do the models in Part B describe the point of intersection of the graphs that you estimated in Part A? So we'll see. Ready? So we have the models given to us. So this is problem 68 on page 839. We have 4.3x plus y equals 198. And the next one is y equals 19.8x plus 98. So they want us to determine the point of intersection where the two lines meet. By the way, do they meet? Yes, of course. We saw the graph, right, of the two lines. So it's the case number one, in which there is one point of intersection. So what would you recommend we do? Elimination or substitution? Look at the two equations and you will realize exactly what we need. What do we need?
seems like substitution.
Right, it's because it's already solved for y.
That's a messy.
Exactly. That's also true. But we can always multiply by 10 both sides. Okay, but this is a very good point. So then 4.3x plus 19.8x plus 98 equals 198. What is our next step towards solving for x? Yes, but first I have to combine like terms, but yes, at the same time I can subtract 198 minus 98 and I get 100. But also on the left-hand side I have, is it 24.1? Correct me if I'm wrong.
Yeah, that's right.
So then x will be 100 divided by 24.1. And x is the number of years since the year 2000. And they asked us to round. They said round to the nearest, use these models to determine the year, round it to the nearest year. So what did we get when we divided 100?
4.15 approximately.
Okay, so if x is approximately 4.1 years, then we will say indeed 2004. But this is good, but we are not finished, right? So what do we have to do next? Next, we will have to determine the x value of the point. So now we have to determine the other coordinate, which is the y coordinate, correct? Okay, so in y we have 19.8 multiplied by 4.1 plus 98. And for that, they want us to round how many millions of customers, round it to the nearest 10 million. So 19.8 multiplied by 4.1 plus 98. I got 179, 179.18 million. So round it to 10th, what would you say? Because this is like 179.180000. And it tells us to round to the nearest 10 million.
180.
180 million. So then what we conclude? What do we conclude? We conclude that it's a good model for the situation we looked at or not. And that's what we read, right? 2004, potentially 175 to 180. We didn't know the answer, but we estimated from the graph. Correct?